We can make this pretty quick. We got this done pretty quick last period. So we did some pretty cool stuff yesterday, but something happened that caused our data to be off by just a little bit. You might remember what the graph looked like was something like this. Something like this. We ended up with our data. Yeah, our data. Is that right? Yeah. Okay. Our data looked like this. It was linear, which was great, but it missed the origin. Okay, it missed the origin by a little bit. And I can't remember if it would have been. Check one thing real quick. Okay, so yeah, it looked like this. It looked kind of like this. Now, think what this is saying. So it makes sense that this is linear, but what this is telling us is that, well, let me ask you this. What would you expect? You'd expect this to be proportional. As the force decreases, it makes sense that the acceleration should decrease too, right? And not surprising, maybe even that it's linear. What do you think should happen if the force, and the force for us, remember, was just that hanging mass. The weight of that hanging mass is what was driving this system, right? What would you expect to happen if the driving force was 0? So if we didn't apply any force to the cart at all? Nothing, right? Okay, so it shouldn't probably accelerate. All right, if the force is 0, the acceleration of the cart shouldn't be something positive, though, should it? Right? That makes sense? By the same token, if the acceleration were 0, that shouldn't correspond to a negative force of some kind, right? We shouldn't have to push on the object to prevent it from moving, correct? So we're off a little bit, right? Okay, what do you think might be responsible for that? Ideas. Do you have an idea?
The cards have the force on the cards.
Still really rounded.
Okay, that's possible. But we had pretty tight linear correlation, right? Table uneven. Okay, but I did adjust before you were here, I adjusted the track so it were leveled it. Okay. Now let me kind of repeat what we did. So we said, for example, that that if I hung, what did we say here? We hung different masses, right? And then we pulled the cart that had a fixed mass, correct? Okay, and so we said that as we hung different weights from this thing, the mass stayed the same of the cart. Okay, so by that logic, then, what do you think should happen if I increase if I decrease the force a great deal? The acceleration should get much smaller, right? If the driving force goes to 0, what should the acceleration go to? It should go to 0. Okay, but then by that logic that we applied, if I were to make the force very, very large and the cart's mass very small, what should happen? It should accelerate really fast, right? So for example, if I applied 1,000,000 newtons of force to a cart that only had a mass of like 1 gram, we should see accelerations that are phenomenally large, right? I mean, that would like shoot through all the walls into the clear across Pendleton kind of thing, right? Agreed? I mean, we could do that. Okay, so if we're creating that force by hanging a weight, are we ever going to see that happen? I mean, what if I had, for example, let's just say hypothetically that we were hanging a mass here that was like 1,000 kilograms, and the cart only had a mass of 1 gram, right? by the reasoning that we employed, we should be accelerating that cart at phenomenally high accelerations. The cart is rigidly, okay, it is, it's rigidly coupled to the mast by a string mill. They always stay the same distance apart, right? So in order for the cart to accelerate at those phenomenally high accelerations, wouldn't the hanging weight have to also accelerate towards the ground at phenomenally high accelerations? Okay, does that happen? If I were strong enough and I could hold a 1,000 kilogram mass in my hand and let it go, what's it gonna look like? Isn't it just gonna look an awful lot like that? Right? Would you agree that if I dropped a bowling ball and a marble, they would hit the ground at the same time? Even though the bowling ball has a lot more mass, it weighs a lot more force is driving it, right? So something's wrong with our thinking here, isn't it? Because that doesn't happen. So we made an assumption there that wasn't good. I made it for you, but you didn't catch it. What's the problem?
Like, since it's just gravity pulling the weight, and like if you were to shoot a bullet or something, then it'd be a lot faster than gravity, because it's known to reach a certain point.
Right.
That's the acceleration.
Okay, you're right, it is. Okay, but then but still, if I took data on this though, and I made the mass like 1/10 of a gram, and we had whatever weight we had hanging from this yesterday, I think we went up to like 200 grams or something. I'm not gonna get a linear relationship there after a while though, right? Because if I increase this mass a whole bunch, I'm kind of running up against what upper end for the acceleration of the cart and the mass? What's the biggest acceleration I'm ever going to see? 9.8, right? Okay, well that can't be right though, because we know that we've seen situations like a bullet, right? In a rifle, it gets accelerated at a lot greater acceleration than 9.8, right? Gravity is just a force like any other force. Right? I mean, I'm telling you right now, 1,000,000 pounds of gravitational force is no different than 1,000,000 pounds of force generated by a magnetic field or a spring or an explosion. Force is force. What did we do wrong? I'll say what we did again. We had the assumption that if the mass of the cart that's roughly, I don't know, like 1.5 kilograms, right? And I hung from this, let's just to make things easy. Let's say that we had a 1 kilogram cart and we had a 1 kilogram hanging mass. That corresponds to a 9.8 Newton force. So we said that, okay, that 9.8 Newton force is acting on 1 kilogram to cause an acceleration. The 1 kilogram of the cart, right? Okay, that can't be right though. Can't be right based on what we just observed. Right? Because if that's right, then if I made the cart 1 gram, I should see a corresponding increase in the acceleration of the whole system. So let me ask you again, is that 9.8 Newton hanging weight acting on 1 kilogram? If I have a 9.8 Newton hanging weight and a 1,000,000th of a kilogram over here, is the 9.8 Newton weight accelerating only the 1,000,000th of a kilogram cart? What do you think? Friction. Okay, friction. True, there is some friction, but it's really small. It's a good idea, but that's not the answer.
Is it because the weight's acting upon the string so that motion doesn't go like, the motion of the force doesn't go like straight to the right or straight to the left, it goes down?
No, it doesn't, because it's a good question, but that's the purpose of the pulley. The pulley redirects the force, right? And we'll look at that in more detail when we get kind of further into this chapter and we look at some vector problems. But I'll tell you right now, you can just take this for granted, that the force, the tension in the rope is the same everywhere. And the tension is what is pulling the cart. Okay, that's a true statement.
Because gravity is also what affecting the,
Okay, I mean, yes, but would gravity affect the cart if it were hovering magnetically? I mean, it's pushing it down, but is that affecting the motion horizontally? And even now, this cart has such low friction. If I give it a little push, yeah, gravity's acting on it, but it sure doesn't look like it's doing much, does it? Right? What is it? There's something else going on here. Okay, explain this to me. If I drop a marble and a bowling ball at the same time, they hit the floor at the same time.
There comes a point when they both reach the same
Terminal.
Okay, but terminal velocity wouldn't happen. That's not gonna happen.
small.
Yeah, that takes quite a ways to happen. To reach terminal velocity, the thing has to be going fast enough to where air resistance becomes really significant. It never did in this experiment. Promise you, it never even came close. Okay, but why is it now? That doesn't seem right in a way, does it? That the bowling ball and the marble, which one weighs more? Bowling ball weighs a ton more, right? So the force that's pushing it down should accelerate it a lot more.
Isn't it acts on it more because of,
What do you think?
isn't it just because it's just acting on the weight?
Say it again. Say that, because what is?
Gravity's just acting on the weight there.
Okay, yeah, you're right. Gravity's only acting on the weight. That's true.
Because the bowling ball weight, like, it doesn't matter how much it weighs.
Okay, right, but why is that though? Because the bowling ball has a much bigger weight acting on it. What do you think? If I take a bowling ball and I roll it down an incline, down a ramp, it doesn't fall, it doesn't accelerate as fast though. Why? Okay, well, even ignoring friction, even if it slid and didn't roll,
It takes more energy to get up to speed.
okay, we don't need energy here. What's happening? What's effectively happening to the force that's acting on the bowling ball if I put it on a shallow ramp? Imagine holding the bowling ball up on a shallow ramp. I can sit here and hold it with one finger, but if I have to hold it straight up and down, I got to use two hands. So the force acting on the bowling ball is decreased. Would you agree when it's on a shallow ramp? And that's why. Okay, that makes sense, and that's why it doesn't accelerate as fast. Oh, okay, right. Okay, makes sense? So, once again, why is it that the bowling ball hits the ground at the same time as the marble, which has a much smaller force? There must be something else going on, right? If I apply a small force to the bowling ball by putting it on an inclined plane, the acceleration is a lot smaller. What's happening? Is the mass that's being accelerated by the hanging weight only the mass of the cart? Okay, go back to the other question. Why does the bowling ball not accelerate faster than the marble? It's got so much more weight. Is that weight accelerating the same mass as the marble?
How would that happen?
See what I'm saying?
Is it the size of the bowling ball?
No, not really. Okay, would you agree if I stack more masses on the cart, it accelerated more slowly, didn't it? For sure. There's a connection between mass and acceleration of some kind, isn't there? We know that, right? Okay. So then tell me, I dropped the bowling ball, I dropped the marble, they hit the ground at the same time. Why? Why does that bowling ball not win that race by a mile? It's got so much more force acting on it.
Doesn't matter, it doesn't accelerate the same as-
You're right, but why?
Because gravity.
No, it's not. That's not it. The bowling ball definitely has a lot more force acting
We're not denying.
Force is mass times acceleration.
on it. No, close. Okay, I'm gonna tell you something different here. I want you to get this. You'll get it. I'll give you another clue. Give you another clue.
No
Okay.
one's leaving this room.
Okay, so now let's say we agree that 9.8 newtons is the force that's driving this system, right? When I hang a 1 kilogram mass that's attached by string to another kilogram mass cart, right? If I were to apply magnetically a 9.8 Newton force to just the cart, and I wish I had it set up, I don't have the capacity to do that, but if I did, you would notice that the cart would accelerate quite a bit, at a quite a bit greater rate than it did when we hung the mass. In fact, it would be twice as
Is
much.
that all you want us to say is because the thing's affecting the thing and the thing?
So now, okay, now, say thing a few less
The
times.
weight, the weight and the cart, is that all you wanted the whole time?
Yeah, but no one said that. That's a big deal.
Well, I thought it was kind of self-explanatory.
Okay, but then I don't think it was, because why is it then answer my question, why does the bowling ball hit the ground at the same time as the marble, even though it's got a lot more force acting on it?
They're both being active.
Okay, but what else does it have a lot more of? Mass. Yeah. It's got a lot more force, but it has to accelerate all its own mass, right? You see what I'm getting at? So what was wrong with our experiment? We did something fundamentally wrong then, right? We assumed in our experiment that the hanging mass provided a force that acted only on the cart. What did we forget to include?
The mass is still.
The mass of the hanging mass, right? Because isn't that a part of the system, right? Now this makes sense. Now we can reconcile why it is that if I have a 100 kilogram hanging mass in a 1 gram cart, that the system only moves at accelerates at roughly 9.8, right? Because the cart doesn't even matter, but the hanging mass still has to accelerate itself, right? And it can't exceed, because its own mass is going to prevent it from accelerating at more than 9.8 meters per second squared down. See what I'm getting at? Okay. Yeah, so that didn't work very well. We wouldn't have gotten good data if we had continued to add masses to the hanging mass. If we had had the capacity to add a tremendously large mass to that, we would have started to see things become really strange and not at all what was predicted. This would no longer have been linear, right? What should we do? How could we, let's say, I'm going to get you started here. You have an idea?
Yeah.
What do you think?
Keep the same amount of mass on the end of the string and then just change the mass on the cart.
Very good. So why don't I just do this? Why don't I just stack a bunch of masses on the cart, and then that's the mass of the whole system, right? If I want to increase the driving force, I'll take a mass off of the cart and put it on there. Hang it, right? Then the mass that's being accelerated, because it's all hooked together, is the mass of the cart and the hanging mass. They're both moving in concert, right? See what I'm saying? Right? Okay, so now I need a volunteer. Let's do this quickly, and we'll see something really cool happen. No.
She took your chance.
Who's it gonna be?
DJ volunteers.
Volunteer here in S tribute.
I got the question right.
Then that's right, you win the opportunity. That's pretty good. Okay, so let's start with, I need a recorder to record our data. So this is the data for is that 20 grams? So
Yeah,
0.02 kilograms. We'll just assume everything is as it's stated on the mass. It's gonna be close enough for our purposes. Okay, that's good. Just hang it there. I'm gonna go ahead and move it up a little bit so it stops swinging. There we go. Okay, now let's have you catch it at the end. Let's see what happens. Okay. Good. So would everybody agree there, if I were to take, I'm just going to grab, I'm not going to make this look pretty. Oh, whoops, screen's frozen. Thank you. That's what it looked like. If I just grab, I'm not going to make it look pretty, but if I just grab that piece of data right there, pretty clearly that's going to be all data that's taken when the card is moving freely, right? Okay, so then we'll just fit that. So we get recorder for our first observation here with 0.02 kilograms. We got a slope of 0.07388 meters per second squared. Okay, so write that down, please. Oh, that's, who is that? That's Ezra? Okay, I was looking at Sydney.
Way to go, Ezra.
Okay, so. Okay, recorded. Now, would you mind trading weights for me? Let's put the, you probably already did, put the 20 back on here and let's add the 50 as a hanging weight. Is that the 50 or is that the?
Is it 50?
Okay, good. Maybe you can kick that string out of there. There we go. So, oops. Okay. There we go. Okay. Thank you, whoever's got that there. Okay, so I'm gonna get, everybody agree that's probably a good section right there? Okay. So our linear fit now for 0.05 kilograms, we had a slope of 0.1889 meters per second squared. Okay, so now we're jumping up to 100.
Almost lost my job.
Yes, you did. Okay.
Pretty funny.
All right. Here we go. Is that? Okay. 0.3928 for 0.1 kilograms. Okay, you got 200 on there?
Yep.
All right, this one's going to go a little faster. Okay, try not to touch the table. I'll try not to do that too. Okay. So I'll just go from, look right there. Okay. For 0.2 kilograms, it's 0.7675. Is this the 500? This is Big Daddy? All right.
Oh, string.
Oh, did it break?
Yeah.
Okay. It's all right, I've got more. You guys should all know how to type roll. It's like the greatest knot ever. Okay. Oh, I did it again. What? Is it, what am I doing? Is it coming up to the, what's causing this? Well, it's, I can't do that because they'll change the results, but it worked last period, so I think it'll work. Tighten it up, tighten it. Let's try that. It's not going to accelerate very far, but it's too good enough. Label that right there. All right, here we go. Okay, well, we got a little bit there. That'll work. All right, so let's go. Right there, how about? 70 again. Right there. All right. Okay, so last one for 0.5 kilograms, it's 1.934 meters per second squared. Okay? All right, so now
Can you say that one again?
1.934.
Okay, thank you.
Okay, so let's go. Okay, so let's see. Give me the accelerate. We want the x to be acceleration. So, what was our smallest acceleration?
0.07388.
0.7388.
0.0.
Oh. 0.7388. Okay. Next one was
0.188.
okay. Next one
0.3928.
Next one.
0.7675.
Last one.
1.934.
Okay, so now I'm gonna convert the hanging masses into newtons. So the first one was a 20 gram mass, right? Okay, so that was 0.0196. Oops, you're right. Messed it up. Okay, next one was 5, so that's 0.049 was 50. And then we had 100, which is 0.196. Oops. And then we had 200, right? No. Well, 100 was, sorry, that should have been 0.098. No, I got that messed up, didn't I? Hang on a second. 50, 100 grams should be 0.98. I got that backwards. Yeah. Yeah. So that's 0.98. And that's 0.4. Yeah. And that's 0.196. Yeah, there we go. Okay, and then we had 200, which was 1.96. And then we did half kilogram, right? 500? Okay. Okay. So now, let's see what this looks like. So there are points. Let's go ahead and calculate, let's use linear regression. And we'll store this as y1. Okay, look at our correlation coefficient. That's pretty awesome. That's very close to 100%. So this is a very good linear fit. So if we look at the graph, that looks pretty good, right? If we look at the equation of that graph again, what's the slope? 2.53-ish. Okay. Okay, and it looks very linear. And notice that, what do you notice about the y-intercept? Very small and slightly positive, right? But almost zero, very close to zero. So if we graph this, then, if we were to talk about what this graph looks like, it looks kind of like that, doesn't it? Right? Everybody agree? Okay, so if it's a straight line that goes through the origin, how do we describe that? How are those two variables, f and a, related? If I graphed force versus acceleration, that's what we saw, right? Because we input the acceleration values for x and the force values for y. So how do we describe a linear function through the origin? Okay, but what's b?
B is 0.
Okay. So remember talking about that as direct variation? Right? The direct variation is what we see when we have a line through the origin. That direct variation, remember what that means. If you double one quantity, you double the other quantity. If you triple one quantity, you triple the other quantity. In other words, they are, starts with a P.
Parallel.
No.
I just know force equals mass times acceleration.
No, you're right. That's what we're going to find. But that's what we call, they're proportional, right? Right? Is that, so maybe this is good math for you too. This is a good way to think about it. It's a good model for this. If we double the force, we double the acceleration. That's what we saw, right? They are proportional. So here's how we say proportionality, right? F is proportional to A, but that's not an equation. If we want to come up with an equation, what's it going to look like? Force equals, well, just mathematically though, we'd say that force equals, maybe not exactly A, but it's some constant times A, right? Because if I double F, I double A, right? If I cut F in half, I cut A in half. So we'll just call it K times A, where K is a constant of proportionality, right? Okay, well, what did we find the slope of this to be? It was 2.503-ish, right? So of that line, what do you think we're going to get if we add up all the mass of this system?
2.5.
About 2.5. It's a little bit, I think we did it last period and it was a little bit less. It was 2.4 or something, but it was close to 2.5. So, is that an accident that the mass of the system has about the same value as the constant of proportionality, which is really just the slope, right? Isn't that all that is? That's the slope of the function, right? So, does that make sense? Yeah, kind of, doesn't it? I mean, doesn't it make sense that there's gotta be something that's providing a physical embodiment of that constant of proportionality? We're not surprised that if we double the driving force, we double the acceleration, right? So then what do we call that thing, that constant of proportionality? Well, conceptually, that's inertia, right? And we haven't talked about that yet, that's coming up. But would you agree that if I were to paint a bowling ball exactly like a soccer ball, that'd be a dirty trick to play on somebody? Because when they ran up to kick it, it's gonna be a problem, right? Why is it gonna be a problem? Okay, because it's got a lot more mass, yeah, and then you might say it's weight, but it's really not weight, because I could do the same experiment in space, where they both have a weight of 0, right? There's no force acting. And I would have the same result. If you fired your retro rockets and went in there to kick them both, you still would break your foot if you kicked the bowling ball. Even though it has 0 weight, it still has a lot of mass, or a lot of inertia, we might say, right? Conceptually. Inertia is an object's resistance to changes in motion, right? To acceleration, in other words. So inertia is a concept, but mass is sort of the quantifiable way of measuring that quantity, right? So mass is our measurement of inertia, right? That's pretty cool. This is a big deal. So we come up with the equation then. We know what the constant of proportionality is. It's mass, right? And so we come up with Newton's second law, F equals ma. Force, not surprisingly, is a vector because acceleration is a vector. Is mass a vector? No, it's a scalar. Just all you need to completely describe a mass is a number, right? What is it that this inertia does then? I mean, what causes it? What do you think? I mean, we're running out of time, but interesting food for thought for the weekend here. What is it that causes the bowling ball to have so much more inertia, aka mass, than the soccer ball? Okay, it's density. You might say density is a good word. Density talks about how much mass is stored in a certain amount of volume, but once again, density relies on the concept of mass, right? So what is it really? I mean, what's going on there? That's an interesting topic. I mean, what causes, what's inherently different about that bowling ball than the volleyball?
Is there a right answer?
Well, yeah, there is. I mean, there kind of is.
So we already know it.
I think you do. There's not like a one-word answer that I think is gonna, well, maybe I guess I probably have a really good word for it, but I mean, does it make sense to you in a way that there's just more stuff in that bowling ball than in the volleyball, or the soccer ball, right? And by stuff, probably we're talking, our physics word for stuff is matter, right? So there's more matter that's sort of concentrated in that bowling ball than there is in the, right? Okay, so therefore density is really a pretty good word, right? But somehow the universe seems to have, and we'll talk more about why this is the case, the universe seems to have a way of recognizing the amount of stuff in an object, and the amount of stuff in an object is what gives it inertia. Okay, the stuff can take different forms. We could take a kilogram of styrofoam and a kilogram of lead, and they look very different, whether we're on the surface of the earth or in space, right? But if we somehow were able to grind those things down to subatomic particles, you'd have the same pile of subatomic particles, right? They're just put together in different ways. Lead is an element, and lead has some properties. The atoms of lead are made in a way that's different from the atoms of styrofoam, so that a lot of stuff gets packed into a relatively small place, right? But still, it's the stuff quantified as mass that is moderating this relationship, right, between the force acting on something and the acceleration that you see, right? Interesting, it really is. And if we had more time, we kind of did this last period, for some reason we had more time left over. We talked about some, the more bizarre forms that stuff could take, and they get pretty bizarre. But topic for another day, I guess. Make sense? So we did something good. That's important. We just, and that's pretty amazing, honestly. I gotta tell you, as somebody who's taught physics long enough to know what it was like to teach physics back in the day before we had nice equipment like this, that is spectacular. That result is amazing. I mean, to be able to get something that's within, far less than 1% of deviation from what we'd expect to happen. I mean, back in the day when we were rolling carts around and using ticker tapes, and they were not very good carts like this, and oh my gosh, if we got within 20%, we felt pretty good about ourselves. That was a pretty good deal. But this makes it a lot more fun when you can actually see good results like that. All right. Have a good weekend. Next week's gonna be a real killer for you. It's a long one.